Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be talking to you about the Common Base NPN BJT amplifier. And this amplifier could be used for many different applications, including the cascoding in analog design, for current buffering. If you're trying to get a current gain close to 1 or close to unity, similar to something like the source follower, but it acts like a current buffer. And lastly, it could also be used for things like wide bandwidth applications, so for like RF amplifiers. And essentially in this video, we're going to try and solve for these three things: Rin, Rout, and AV. And if you want, you can pause the video and see if you can solve for these, and then come back to the video and see if you get the correct answer. But first, we want to acknowledge why we call it the common base. And essentially that is because in the circuit, this is the base, this is the collector, and this is the emitter. And in this circuit, the base is the one that is grounded or is common to the circuit. And we can then go ahead and solve for Rn. So I redrew the circuit here. And what I'm going to do is for it to be visualized a little bit easier, I'm going to consider that if I have this V in here, it's the same drop V in over here. And as a result, this current here, I can delete this, right? And this current here can be considered IN. So I hope that makes sense. I'm going to put it back the way it was, just because we need it for analyzing. So this is VN. So the first thing, we want to write a couple of equations using KVLs and KCL equations, using circuit analysis. So the first thing we want to say is that in order to solve for Rn, we need to realize that Rn is equals to Vn over In when Vout is equals to 0. Or essentially you short Vout to ground. So what I'm going to do is I'm going to erase Vout. I'm going to short it to ground. So since this is shorted to ground, this is also shorted to ground. So as a result, this entire thing goes away and this is just grounded. Maybe pause the video and make sure this makes sense. So we can start by writing a KVL here. So I'm going to draw a line here and call this 1. And I'm going to say that plus VBE plus Vn is equals to 0. So this is my first equation. And what I'll do is I'm going to solve for VBE is equals to minus Vn. And then I'm going to consider a KCL. So this is equation 1. I'm going to consider a KCL of this IN. So IN goes in here, IN1. And then obviously it flows out here, IN. I'm going to say then that IN, right, this is another equation. This was my first equation. I'm going to say IN is equals to minus GM VBE plus IN1. And let me go ahead and solve for IN1. So IN1 is equals to IN plus GM VBE. As a result of this, we get this is equals to IN plus GM. VBE is equals to negative Vn. So this is minus Vn. And this is equation 2. So then the last equation we want to write is this loop here. Or we can take it the other way. Since this is Vn, we could take a loop here, a KVL. And I could say then that there's an equation minus Vn plus RO I in 1 has to equate to 0. V in, I can move to the right hand side, but I'm going to write it on the left. I can say V in. Well, actually, let me plug things in first. So V minus V in plus RO I in 1 is I in plus, or better say minus GM V in, which is equals to 0. Let me go ahead and distribute RO. So this is minus V in plus RO I in minus GM RO V in has to equate to 0. And let me move all my V in terms to the left hand side, but I write it on the right hand side. So V in plus GM RO V in has to equate to RO I in. And then this becomes V in 1 plus GMRO is equals to ROI in, or R in, which is equals to V in over I in, is equals to 1 plus GMRO over RO. In many situations, we consider channel length modulation to be 0, so gamma is 0. This considers RO to be infinity. And we say then that Rn is equals to 1 plus GM times infinity over infinity. Again, this 1, there was a mistake here that I made. This should be opposite. So essentially, this should be RO 1 plus GM RO. And on the bottom here should be infinity 1 plus GM times infinity. As a result, this cancels out. So then this is approximately 1 over GM. All right, so I hope this makes sense. And this is how you get the Rin, or the input resistance of a common base amplifier. So let's go ahead and move on to the output resistance. And similar to the input resistance, we know that for the R out, let me zoom out a bit. For the R out, this is V out over I out when V in is equals to 0. So what we can do is we can consider that this goes out of the picture and it just gets shorted to ground. We can also consider something here, something interesting here. We can consider that the drop across RL is VO. As a result, we can take this out and we can consider this current to be I out. And if that doesn't make sense, another way to look at it is in this device, this is AC ground. As a result, the drop across RC, so this is a high potential, this is a lower potential. So the current going in here is I out. So I hope that modification makes sense for our analysis purposes. So we can then write the same exact steps we did before. So I'm going to write a KVL here, call this 1. So I'm going to say then that VBE is equals to 0, plain and simple. I'm going to write a KCL for IO, similar to how we did in the previous example. Again, this is equation 1. I'll say that IO is equals to IO1, or the current that's going in this direction, plus GMVBE. And as a result of this, IO is equals to IO1 plus 0, because again, this goes to 0. So then, or just IO1. And this is my equation 2. And then the last equation I'm going to write is an equation, or KVL, at this loop. And I'm going to say that minus VO plus ROIO1 has to equate to 0. And VO is equals to ROIO, because, again, I'm moving this to the right-hand side, so it becomes positive. And IO is equated to IO. No, IO1 is equated to IO, as shown here. And essentially, R out, which was VO over IO, is equals to RO. So this is my R out equation. So I hope that makes sense. If you didn't receive this, please let me know down in the comment section if you need help in further explaining how to get this. Please let me know down in the comment section below. Otherwise, we're going to move on to the last portion of this lecture, or of this video, and we're going to talk about the AV gain. Now, the AV gain, so AV considers VO over VN. So we're going to need to write certain KVLs and KCLs to solve for this. The first thing I'm going to do is I'm going to, again, modify this circuit. So I'm going to cancel this VO, and I'm going to say that it goes across this RL resistance, which it does at AC analysis. And there's a current source IO that goes there, and a current source IO1 that goes right there. I'm going to start by writing a KCL for IO. So IO is equals to 0 minus V out over RC. So I hope this makes sense. This would be minus V out over RC. This is equation 1. I hope this makes sense. So I'm basically taking a lower potential at 0 volts and minus a higher potential at VO and dividing it by RC. So that's all I'm doing there. Let me make this smaller. So the next step is I'm going to write a KCL for IO going in here, here, and here. So I could say then that another equation I can write is that IO is equals to IO1 plus GM VBE. Okay, and I can call this equation 2. So then let me start writing out my KVLs. I can write a KVL here. Let me call this 1. So the KVL says that VBE plus VN has to equate to 0. So VBE is equals to minus VN. Using this, I'm going to plug this into here, and I'm going to rewrite my IO as IO1 minus GM VN. And lastly, I'm going to write IO1 as IO plus GM VN. All right. And then the last equation I need to write is a KVL here. Call that 2. And I'm going to say then that minus VO plus ROIO1 plus VN must equate to 0. So minus VO plus ROIO plus GM VN plus VN has to equate to 0. This becomes minus VO plus ROIO plus GM ROVN plus VN is equals to 0. This then becomes minus VO plus RO. IO, I made a mistake. This is IO1, IO1. RO is IO plus GM. Oh, no, I didn't. I didn't make a mistake. So this is IO. So what I meant to say was that this should be RO. IO is this equation. It's VO over RC plus GM RO VN plus VN is equals to 0. There's a negative here. So then let me move the V outs to the right hand side. This becomes V out 1 plus RO over RC. Maybe pause the video and make sure this makes sense. This is equated to VN 1 plus GM R out. Let me go down. I didn't want to move the circuit out of the way, but it looks like I need more room. So let me go ahead and write AV, which is going to be VO over VN as 1 plus ROGM over 1 plus RO over RC. When we consider when RO is much greater than RC, we can consider an infinite resistance. AV is approximately, this term is a lot bigger than 1. So essentially this becomes ROGM over RO over RC. Let's go ahead and multiply this entire thing by RC and RC. This then is approximately ROGM RC over RO RC. As obviously the ROs cancel out, and the this becomes just RO on the bottom because this cancels out with this. So then this is approximately GM RC is AV. So again, as you can see, this is your final answer for your AV gain of a common base amplifier. And unlike the common source, which again, I made a video on this, please feel free to check that out. The AV gain for the common source was negative GM RC, where it inverts the signal. This does not invert the input signal. So it's just it's a positive. So you give me a positive signal, I give you back a positive signal that's amplified. So I hope this makes sense. If you have any questions, please let me know down in the comment section below, and I'll be sure to get back to you and respond to them. If you like the video, please like and share the video. Give it a thumbs up, and don't forget to subscribe to my YouTube channel. Thank you, and have a wonderful day. Bye.